In this goal, we are going to learn about mass-to-mass relationships, also mole-to-mole relationships, and we will do this by using a balanced equation. This is also called stoichiometry, but I prefer just to call it mass-to-mass relationships. So to start off with, we're going to do a little analogy. So let's make a sandwich. So the recipe for the best sandwich has 2 pieces of bread, 4 pieces of meat, 1 piece of cheese, and 3 pickles. If I were to put it into a sandwich equation, I would have 2 bread, 4 meat, 1 cheese, 3 pickles, and that would give me 1 sandwich as my product. So let's just kind of go through this. So if you had 4 pieces of bread, what would you need to go with those 4 pieces of bread? So when you compare the 4 pieces of bread to what the recipe says, you see that I have doubled it. So you would have to double everything in order to get and follow the same recipe. Let's look at number 2. What would you need if you needed to make 30 sandwiches? So to make 30 sandwiches, you would, instead of just doubling it, you would multiply it by 30. So you would follow the same recipe, but you would need 60 pieces of bread, 120 pieces of meat, 30 pieces of cheese, and 90 pickles. So you can see that this recipe holds no matter what you have. Let's look at number 3. How many sandwiches could you make if you had, and this is a little bit different. So this one we're looking at a whole bunch of ingredients and figuring out how many sandwiches we can make. And so for this one, if you look really carefully, you would find that you could only make 3 sandwiches. And the reason why is because you do not have enough pickles to make more than 3 sandwiches. So this, in chemistry, this is our limiting ingredient, or in chemistry terms, the limiting reactant. And we are going to talk about limiting reactants at a later time. Basically, your limiting reactant is what is used up first. And because it gets used up, then you're limited with how much product you can make. Balanced chemical equations are exactly like a recipe, like our sandwich recipe. We use moles to see ratios in reactions, and it's very important to have a balanced chemical equation. And most of the chemical equations that are given to you in your homework, they will already be balanced for you. So we use the balanced chemical equation to determine how much product is made from a specific reactant, or how much of each reactant will react together. Let's look at a sample problem. So looking at our reaction right here, we see that 1 molecule of CH4 reacts with 2 molecules of oxygen, and my products are 1 molecule of carbon dioxide and 2 molecules of water. It's a very classic combustion reaction. So just dealing with molecule units, so 1 molecule plus 2 molecules, that's really, really small. So instead, we look at it with much larger quantities. We look at it in quantities of the mole. So I have 1 mole of this methane, and the 1 just isn't written. So if they just write the formula, then you know that the 1 is assumed. And I have 2 moles of the oxygen. And for my products, I will get 1 mole of my carbon dioxide and 2 moles of my water. So this is the recipe. A 1 to 2 ratio of reactants yields a 1 to 2 ratio of products. And it doesn't always turn out the same this way, 1 to 2 and 1 to 2, but this is an example that does. All right, we're going to use the balanced reaction to help us determine relationships between reactants and products, or maybe 2 reactants. So let's look at our first problem. So our first problem, you want to find the number, and it says right here, 6 moles of oxygen. So this is our starting point. So I'm going to write 6 moles, and I'm also going to include oxygen. And let's look and see what we're going to convert this into. We're going to convert this into moles of CO2. So our goal is to go from oxygen to CO2. So to go from a mole of one substance to a mole of another substance, you need to look at the recipe in that balance equation. So the two things that I'm looking at are oxygen and carbon dioxide. So I'm starting here and I'm ending here. I am going to use this recipe in my conversion equation. So I want to cancel out moles of oxygen and I want to change it to moles of CO2. And looking at the reaction, I see that it is a 1-to-2 ratio. So remember these conversion factors, they have to be equal to each other. Whatever's on top has to be equal to whatever's on the bottom. When you are going from mole to mole, you are using your balanced equation to write a ratio. So again, the ratio is kind of like your recipe. So let's go ahead and do the math. We have 6 times 1 divided by 2. I have 3 moles. So maybe another way that you can look at this is for every 2 moles of oxygen, I only have half as much CO2 because there's only a 1 over there. So if I have 6 moles of oxygen, I should have half as much of CO2, and that is correct. And our conversion factors show this, that moles of oxygen will cancel and I'll be left with moles of carbon dioxide. Let's look at this next one. So in this next one, we're combining what we learned in goal 2, doing grams to moles and moles to grams. And we're just going to add a step in the middle where we look at the balanced equation. So start with the number that they give you. So 48 grams of methane. And so with this one, I'm just going to kind of erase up here. So with this one, we are going to go from methane to, well, let's see, grams of water to water. Okay, so we're starting here, we're ending here. That is our goal, from methane to water. And we start out with grams of methane. Now, 1 gram of methane does not equal the same amount of atoms as 1 gram of water because our methane molecule and our water molecule, they're different sizes. And so we can't compare grams to grams, but we can compare moles to moles by using our equation. First, we need to get to moles. So I'm going to cancel out grams and change it to moles. And recall from the previous goal that 1 mole of anything is equal to the molar mass. And we get this from the periodic table. So looking at the periodic table, I can add up 12 grams per mole for carbon, and each hydrogen is a 1, and I have 4 of them. So that gives me a grand total of 16 grams of methane. So grams of methane cancel, and I'm left with moles of methane. So this you should know how to do from before. So now we're going to switch from working with methane to working with water. And to do this, I'm going to use the balance equation. So I'm going to put moles of methane down here and change it to moles of water. And then the numbers that go in front here come from the balanced equation. So you see that I have a 2 here, and that comes from this 2 in front of the water. And I have a 1 here, and that comes from the 1 that's in front of the methane that's assumed. All right, so my moles cancel, but so does my methane. So now I am left with moles of water. And I just use my previous knowledge, and remember, 1 mole is equal to the molar mass in grams, looking on the periodic table. So I want to cancel out moles of water, and I will add up the molar mass of water looking at the periodic table. So I have 2 hydrogens, so that's 2 times 1, and I have 1 oxygen, which is 16. So that gives me a mass of 18. All right, so my units all cancel, and I am left with grams of water, which is what I want my answer in. And we just need to go and do our math. So every time you go across, you multiply, and every time you go down, you divide. So we have 48 times 1 divided by 16 times 2 divided by 1 times 18 divided by 1. And when you work this out, you get 108 grams of water. Okay, So what did I do? I first converted from grams to moles. So grams to moles. The next thing that I did is convert from moles to moles using the balance equation, and then I converted back to grams of my new material. So grams to moles using the balanced equation, and then lastly back to grams. And it always has this pattern. So if you look down below, you see that I divide by the molar mass first, then I multiply by the ratio from the balanced equation, and I make sure my units will cancel. And then last but not least, I multiply by the molar mass of my new substance. And then I just multiply and divide. You can do this in 3 steps. So I can convert grams to moles, find an answer. Then I can take that answer and multiply it by the ratio from the balanced equation. And then my third step, I can multiply it by the molar mass of my new substance. So I want you to look at problem number 1 and problem number 2. Problem number 1 is exactly like the example that I first gave you, where you just do moles to moles. And problem number 2, you're going from grams to moles, and moles to grams. So go ahead and try both of these problems. And so stop the video, and then we'll come back and do the answer. Okay, we're back. So on this first one, you should identify your starting number. So 5 moles of methane. And we are going to convert that to moles of oxygen. So looking at our balanced equation, I'm going to start here and I'm going to end here. So really, we're on the reactant side and just seeing how they react together. So start with your starting number, so 5 moles of methane. And then we are going to cancel out methane and change it to water. Or excuse me, change it to oxygen. And so we're really just doing this middle step right here, this mole to mole step. And so when I look at the ratio, I see that I have a 2 moles of oxygen to every 1 mole of methane. So moles cancel and also methane cancels. And so I am left with moles of oxygen. And so I just do my math. 5 times 2 divided by 1, I get 10 moles of oxygen. Now, looking at that balanced equation, we see that for every 1 mole of methane, I need 2 moles of oxygen. So if I have 5 moles of methane, I would need to times by 5. So 2 times 5 is 10. So you kind of can do this in your head, but this is how you work it out, letting your units guide you. And so you'll cancel out your units. So again, I get this ratio right here from this balanced equation. All right, let's do the next one. So I'm just going to erase up here. So let's start with what we're given. So we're given 55 grams of CO2. So this is our start. And it says how many grams of oxygen was used up. So this is our end. So I can be given a product and find a reactant, just like this one, or I can be given a product and find the other product, or given a reactant and find the product, or find out how much 2 reactants will react together. So always start with your starting amount, and we're going to cancel out grams of CO2 and change it to moles. And remember, 1 mole is equal to the molar mass in grams. And so if I add up 12 for carbon and 16 for oxygen, I get 44. So I use my periodic table for that step. So that's my grams to moles step. So I got that step done. So now I have moles of CO2. So looking at the balanced chemical equation, I see that for every 1 mole of CO2, I get 2 moles of oxygen. Moles cancel, but so does the CO2. So now I'm working with moles of oxygen. And now it's just a matter of turning it to grams. And so remember, 1 mole of oxygen is equal to the molar mass of oxygen, which would be 32 grams of oxygen. Because it's O2, not just O. So moles cancel, I'm left with grams of oxygen. And when I do my math, 55 times 1 divided by 44 times 2 divided by 1 times 32 divided by 1, I get 80 grams of oxygen. Okay, so for sig figs, I just want to put a little decimal after that, meaning that both of those count. Okay, all right, so this concludes the grams to moles, moles to moles, moles to grams. So it is 3 steps: grams to moles to moles, and then moles to grams. And remember, the mole to mole step comes from using that balanced equation. So here's some further practice if you need it. So go ahead and stop the video and you can do these problems and I'll come back and do the answer. Okay, we're back. So we're given a balanced equation, and in our balanced equation we see that we have 2 moles of hydrogen for every 1 mole of oxygen that react together. Those are my reactants. And it yields 2 moles of water, which is my product. So let's start off with our 7 moles of hydrogen. So this is the number that we're given. And let's look and see what we need to solve for. We need to solve for moles of oxygen. So in grams to moles to grams, this is the pattern. On this problem, we're just doing the middle, okay? So just the middle for this. So looking at my balanced equation, I have 2 moles of hydrogen for every 1 mole of oxygen. So my moles cancel and my hydrogen cancels, and so I'm done. I have moles of oxygen. So again, I have to use my balanced chemical equation and to get those coefficients, and these coefficients come from the balanced equation, okay? So 7 divided by 5, we get 3.5, okay, moles of oxygen. There is only 1 sig fig, so really you'd probably have to round up to 4. All right, let's do this next one. So we have 5 grams of oxygen, and it says how much water is produced. So we are going to start with our oxygen. There's our start, and we're going to end with our water. So to use the balanced equation, we have to be in moles. So that's always our first step here. So I know that for oxygen, 32 grams of oxygen equals 1 mole. So, and that's because 1 mole equals what it says on the periodic table. And it says O2, so I just add 16 plus 16. So grams cancels, I'm left with moles of oxygen. So now I'm going to cancel out moles of oxygen, and this is using my balanced equation, and change it to moles of water. All right, so moles cancels and oxygen cancels, and now I am working with moles of water. So to go to grams, 1 mole of water equals 18 grams of H2O. So I will have my final unit as grams of water. And so now it's just a matter of doing the math. So I'm going to take 5 times 1 divided by 32 times 2 divided by 1 times 18 divided by 1, and I get 5.6 grams of water.